less delay. Today I'm going to discuss the last topic of this chapter, and here in this topic I'm going to state two theorems, okay, and the proof of the theorem, we will just see the geometrical interpretation, and we will solve few examples on these two theorems, okay. So we were doing this chapter, continuity and differentiability, okay. Now we are going to discuss the last topic, and in this topic we have two theorems, okay. So first theorem we have is Rolle's theorem. Okay, now I'm going to state this theorem, okay, and then we will discuss this theorem, okay. If f is a function which is defined from closed interval a to b. Now closed interval a b means, you know, it is a subset of real numbers, so it's a subinterval in the real numbers. So closed interval a to b means we are taking all the real numbers in between a b and including ab, since it is closed interval, okay, and it is a real valued function. If this function is, okay, number one, continuous on closed interval AB, number two, differentiable on open interval AB, and f of A is equals to f of B, okay, then, or you can write, then there exists at least one C in the open interval A to B such that f dash C is equals to 0, okay. So this is the statement of this theorem, right? What it says is, if you have a function f which is defined from closed interval a, b to set of real numbers, so this is the function domain of this function, okay, and all its images, it lies in set of real numbers. So if you have a function f from closed interval a, b to set of real number, okay, and if this function is now these are the conditions this function should satisfy, okay. So if f is continuous on closed interval ab, okay, closed interval AB, continuous means, now we had already studied when do we say that a function is continuous. So within the closed interval AB, the graph of this function is not broken anywhere, okay. So this function f is continuous on closed interval AB. The function is differentiable on open interval AB. Differentiable means at each point within this interval, open interval AB, a function is said to be differentiable if at that point there exists a unique tangent at that point, okay. So if a function is continuous on closed interval AB, differentiable on open interval AB, and f of A is equals to f of B, the function value at these two extreme points are equal. If this function is satisfying all these three conditions, okay, then there exists, now you know this notation, that is there exists, okay, then there exists at least one C, okay, in the interval, open interval AB. If this function f is satisfying all these three conditions, okay, then there exists at least one C in this interval such that, okay, so this notation is such that, right, used for such that. So then there exists at least one C in the open interval AB such that f dash of C is equals to 0, right? So this is the statement of this theorem. Now we shall see the geometrical interpretation of this theorem. So I can prove this theorem graphically, okay? Okay, so say this is my graph, right? And now you can consider any function. So any function, it represents certain curves you have, okay? So let me take my function as this, okay? So okay, now my function is this, okay, and it is defined in the interval a to b. Okay, now this is my function fx, right? Okay, now you look at the graph. Okay, now you can see within the interval, closed interval a to b, the function is continuous. Graphically you can see the graph is nowhere broken, so this function is satisfying the first condition. Okay, so in the graph you can see that this function is continuous. It is continuous, right? Okay, the second one, the function is differentiable on AB. Differentiable on AB means a function is said to be differentiable at a point if there exists a unique tangent at that point. Okay, now within this interval, if I take any point here, okay, so at this point I get a unique tangent, right? Similarly, if I take a point somewhere here, then at this point, okay, then at this point I can have a unique tangent. Okay, so but at these two extreme points, it is the end point. So at these 2 points you will have infinitely many tangents, right? So therefore the function is not differentiable at these 2 extreme points. So therefore we had taken here open interval. We are excluding these 2 points. Okay, so the function is continuous on closed interval AB, right? The function is differentiable on open interval AB. Okay, now the third condition is f of A is equals to f of B. Okay, so you can see, if I consider here, okay, so this point is A f of A, right? So this is f of A, okay, and this point is B and this is f of B. Okay, so you can see it's the image of this point is f of A, image of this point is f of B, so f of A is equals to f of B, right? So this is a function which is satisfying all these 3 conditions. So the graph of this function, you can see it is continuous on closed interval AB, it is differentiable on open interval AB, and f of A is equals to f of B. Okay, image of A and image of B, they are also equal. Okay, so now what this theorem says is, if a function is satisfying all these 3 conditions, okay, this is your hypothesis, the function is satisfying all these 3 conditions, then what will happen is, then within the interval AB there exists at least one C. At least one C means more than one C can exist, but at least there will be one C such that f dash C will be equals to 0. Okay, now first let me recall this. When in class 11, when you were introduced differentiation for the first time using first principle method, then we say that using the first principle method we have this f dash x is equals to slope of the tangent at this point. Slope of the tangent at the point, is it? So we consider this derivative of x is slope of the tangent at that point. Okay, so with using this concept you had derived first principle method to find the derivative of any function, right? Whether it is a polynomial function or trigonometric function. So the concept is the derivative of a function at a point is equals to the slope of the tangent. So we had used that concept. Okay, so now if this happens, okay, now then you can see at this point, let it be C. Okay, okay, so at this point on the graph you get this tangent, right? This tangent we have. Okay, I'll use okay, now at this point let it be C1. At this point, if you draw the tangent, right, from this point if you draw the tangent, you can see this tangent is parallel to x-axis, right? Similarly, if I see a point here that is C2, from this point also the tangent is parallel to x-axis. If I take a point here C3, at this point also when you draw the tangent it's parallel to x-axis. Okay, now all the points C1, C2 and C3, they lie within the interval AB, is it? So we got here 3 C's such that from this point when you draw the tangent is parallel to x-axis. Okay, And we know that the slope of the x-axis is 0. Slope of x-axis is 0. Okay. So all this now slope that you had studied in class 11 in chapter straight line. Okay. So using the slope of the line, you had derived first principle method for finding the derivative. Okay. So I'm just using this concept only. So f of here, this f dash of c1 is equals to 0. Okay. Because at this point the tangent is parallel to x-axis, so the slope of this line is 0. Okay. Similarly, f of c2 is equals to 0. F of c3 is equals to 0. Right. So here we get 3 c's. Okay. So here in the statement it is stated at least 1 c. So even if you don't get 3 c's every time, but at least you will get 1 c at which the derivative will be equals to 0, because derivative means it is the slope of the tangent. So the line which is parallel to x-axis, its slope is 0. So therefore the slope of this tangent will be equals to 0. Okay, so this is the geometrical interpretation of the Rolle's theorem. Okay, so now you just have to remember, okay, to apply Rolle's theorem. First, the function should satisfy these 3 conditions. That is, a function f is from closed interval a, b to r, set of real number is. The function should be continuous. Okay, now you have to remember the intervals. So the function has to be continuous on closed interval a, b, differentiable on open interval a, b, and f of a is equals to f of b. So first, to apply Rolle's theorem, you have to check whether a function is satisfying these 3 conditions or not. Okay, if a function is satisfying all these 3 conditions, then it means Rolle's theorem is applicable, which means there exists, you can find out at least 1 c. Okay, and that c will be within the interval ab, open interval ab, such that f dash c is equals to 0. Is that clear? So this is the statement of Rolle's theorem. Okay, now we will take one example. Okay, okay, now we shall solve this example. Okay, and you will see how such questions are to be done. Okay, verify Rolle's theorem for the function fx equals to x into x minus 3 whole square, where x belongs to 0 to 3. Okay, in some question you may be given as x belongs to this, or in some questions you may be given as x is greater than or equals to 0 and x is less than or equals to 3. So these two, whether it is given in this form or in this form, the meaning is same. Okay, so you have to check whether Rolle's theorem, okay, is applicable for this function in this interval or not. You have to do that. Okay, now you recall the statement of Rolle's theorem. Okay, so Rolle's theorem is applicable only when a function satisfies 3 conditions, which is number 1, the function has to be continuous on the closed interval. You have to remember the intervals also. Okay, so a function has to be continuous on closed interval, a function has to be differentiable on the open interval, and f of a is equals to f of b. Okay, so if first you check whether these 3 conditions are satisfied or not. Okay, so we are going to do that. Okay, now here you are given function fx is equals to x into x minus 3 whole square. Okay, now first you see what type of function is it. Okay, so you can see that fx is equals to x into x minus 3 whole square, which means x is a polynomial function. Okay, so now we know that polynomial function is continuous everywhere. Okay, polynomial function is continuous on set of all real numbers. So basically here in our syllabus you will be asked to verify Rolle's theorem and mean value theorem, which I'm going to derive later. So you will be asked to verify these 2 theorems only on polynomial functions. Okay, so you won't be given trigonometric functions. Okay, so our syllabus is restricted only for the verification of these 2 theorems on polynomial function. Okay, and you remember that polynomial function is continuous on everywhere, and also it is differentiable. Okay, so now you write this. Okay, since you will write this, since fx equals to x minus 3 whole square is a polynomial function, Therefore, number 1, what do we have? Fx is, you will write this, continuous on. Okay, now look here. Now this is how this solution is to be presented. Okay, so every step it contains marks when you are writing it in the exam. Okay, so you cannot just directly write that it is continuous, it is differentiable. So you have to use correct intervals. Okay, so when you are saying that a function is continuous, then you remember you have to use closed intervals. So you will write, since fx equals to this is a polynomial function, so therefore fx is continuous on closed interval 0, 3. Okay, you have to write this now. Okay, number 2, fx is differentiable on open interval 0, 3. Okay, so this every times you just remember, you just have to write down this. Okay, because you don't have to prove that this function is continuous, this function is differentiable. Okay, since we had did this in the previous topic in continuity and differentiability, you just write down, if a function is polynomial function, it is continuous everywhere, so you can just generalize it. Fx is continuous on closed interval AB and fx is differentiable on open interval AB. Okay, so you have to state this. Since it is a polynomial function, so therefore fx is continuous on closed interval 0 to 3, fx is differentiable on open interval 0 to 3. Okay, now the first and second condition is satisfied by this function. Now we have to check the third condition, that is f of a is equals to f of b. Whether this happens or not, we are going to do it. Okay, now here your a is 0 and b is 3. Okay, so you will find out f of 0 and you find out f of 3. Okay, so f of 0, now this is your fx. F of 0 is 0 into 0 minus 3 whole square. Okay, so that is 0 into any term is equals to 0. So f of 0 is equals to 0. F of 3 is equals to 3 into, okay, 3 minus 3 whole square. So that is 3 into 0. So that is 3 minus 3 is 0. So again it is equals to 0. So therefore we have f of 0 is equals to f of 3. Okay, so now this function is satisfying all the three conditions. The function is continuous, the function is differentiable, and f of 0 is equals to f of 3. So the function is satisfying all these three conditions. Okay, now you have to check whether you get such c in this interval or not. Now we are going to do that. Okay, so what you will do is, first you find out f dash of x. First you differentiate this. Okay, so either you can expand this term. Okay, so that is x into x square plus 9 minus 6x. Okay, so that is equals to x cube plus 9x minus 6x square, right? So you write down this. So that is now derivative of f. Okay, first you write down what is fx. It is x cube minus 6x square plus 9x. Okay, so we have f dash of x is equals to 3x square minus 12x plus 9. Okay, so from this you can take out 3 common. So we have x square minus 4x plus 3. Is that clear? Okay. Okay, so we get this. Now you have to find out such c at which, okay, f dash of c is equals to 0. Okay, now we are going to do that. Okay, so I will rub it. So I hope you had kept the note. So first you find the derivative. Okay, so now what do we have? We have f dash of x is equals to, here this is 3 into x square minus 4x plus 3, right? So first you find out f dash of c. So now everywhere x is to be replaced with c. So you get 3c square minus 4c plus 3. Okay, so now you equate f dash of c is equals to 0. You have to equate this with 0. Okay, so therefore you write 3 into c square minus 4c plus 3 is equals to 0. So this implies now 3. So here we get c square minus 4c plus 3 is equals to 0. Okay, so when you multiply two terms and you're saying that it is equals to 0, then c is a non-zero term, so it cannot be 0. So the only possibility we have is this term has to be 0 to satisfy this equation. So therefore 3 cannot be 0 because it's a non-zero term. So when you multiply 3 and some other term and you get 0, so then the only possibility we have is this term has to be 0. Okay, now this is a quadratic equation, so you know how to solve a quadratic equation. So we are going to do that. So that is c square minus c minus 3c plus 3 is equals to 0. So from these two terms I can take out c common, so the c minus 1 minus 3 you take out common, so c minus 3, okay, sorry, 1 is equals to 0. So I get c minus 1, c minus 3 is equals to 0, right? Okay, so from here I'll do it here. So therefore I get two values, c is equals to 1 or 3. Okay, so either c is equals to 1 or c is equals to 3. Now what should we have is c has to be in the open interval AB. C has to be in the open interval AB. So 1, when I take c is equals to 1, then it lies in the open interval. Now c should be in the open interval 0 to 3, open interval 0 to 3. So therefore c cannot take this 3, is it? So we get only one value of c, okay, which lies in this interval. So therefore we have c equals to 1, which belongs to open interval 0 to 3, such that f dash of c is equals to 0. So this theorem is verified. Okay, so first you will check whether a function is satisfying these three conditions or not. You will do that, and after that you will find the value of c such that f dash of c is equals to 0. Okay, so this is how we are going to do it. So this theorem is verified. When this function is satisfying all the three conditions, then we get one value of c within the interval 0 to 3, open interval 0 to 3, such that f dash of c is equals to 0. So this is how Rolle's theorem is to be verified. Okay, all right, now okay, before moving on to the next theorem, I will take one more example to verify Rolle's theorem. Okay, now I'll take a simple example and you will see the same pattern we are going to follow to check whether the Rolle's theorem is verified or not. Okay, so if I consider fx is equals to x square plus 1 and okay, verify Rolle's theorem for the function. This is example 2. Okay, verify Rolle's theorem for the function fx equals to x square plus 1 in the interval -2 to +2. Okay, so first you check fx equals to x square plus 1 is a polynomial function. So every time you have to write this. Okay, this is how you are going to present this solution. Polynomial function, thus fx is continuous. You have to write this, continuous on closed interval -2 to +2. Number 2, fx is differentiable on open interval -2 to 2. Now you have to take the correct intervals. Okay, and then you have to find out f of -2 and f of +2. So you have to check whether the third condition is satisfied or not. Okay, so this is your A, this is your B. So f of A is equals to -2 whole square x square plus 1. Okay, so that is 4 plus 1, which is equals to 5. Okay, now we will find out f of 2, that is 2 square plus 1. So that is 4 plus 1 is equals to 5. So f of -2 is equals to f of +2. Okay, so now this function is satisfying all the three conditions. That is, the function is continuous, it is differentiable, and f of -2 is equals to f of 2. Okay, now we have to find out in open interval -2 to +2, you have to find out the value of c at which f dash of x is equals to 0. Okay, so we have fx is equals to x square plus 1. So now if you compare the previous example and this example, in the same steps, within the same steps, I'm going to solve this. So you just see, okay, what is to be done one after the other. So fx is equals to x square plus 1. So first you find out f dash x, that is equals to 2x, okay. Derivative of 1 is 0, okay. So we have f dash of c is equals to 2c. After finding f dash x, you find out f dash of c, and then you will equate f dash of c is equals to 0. So which means 2c is equals to 0. So you get c is equals to 0, okay. And this value, it lies in the open interval -2 to +2. So please, you have to take the correct interval, okay. So after finding the value of c, you have to put the value of c in this interval, open interval -2 to +2, right? So you see, when a function is satisfying these three conditions, okay, then you get at least one c within the open interval -2 to +2, whatever open interval ab, such that f dash of c is equals to 0, okay. So therefore you will write thus Rolle's theorem is verified, okay. So in the previous example also you have to write this at the end, okay. Thus Rolle's theorem is verified, okay. So when a function is satisfying these three conditions, then this always happens, okay. So this is the Rolle's theorem, okay, and this is how Rolle's theorem is to be verified, right? Okay, now I'm going to discuss the next theorem, that is Lagrange's mean value theorem. Lagrange's mean value theorem, also it is called as mean value theorem, and in short we write LMVT, Lagrange's mean value theorem, okay. So Lagrange is the mathematician who gave this theorem, so we call it as Lagrange's mean value theorem. Also you just can call this as mean value theorem, okay. So in short you can write it as LMVT. So in some books, if you may find out LMVT, then it means it is Lagrange's mean value theorem, okay. So the statement of the Lagrange's mean value theorem is quite same. So I'm going to remove this, okay, the third condition. So to check mean value theorem, okay, so a function should satisfy only these two conditions. In Rolle's theorem, a function has to satisfy three conditions, right? But here in mean value theorem, a function will satisfy only these two conditions. If a function is satisfying only these two conditions, okay, then there exists at least one c in the open interval ab, such that f dash of c is equals to f of b minus f of a whole divided by b minus a. Okay, so this is the statement of the theorem, mean value theorem. If a function f from ab, close interval ab to r, is continuous on close interval ab, differentiable on open interval ab, then there exists at least one c in open interval ab, such that f dash of c is equals to f of b minus f of a upon b minus a, okay. So we will see the geometrical representation of this theorem, okay. Okay, I'm going to take a Cartesian plane and let me take my function as any curve, and if I consider this in the interval AB, okay, let this function be y is equals to f of x, okay. So this is the curve of this function and now you can see this function is continuous in the closed interval AB and it is differentiable on open interval AB, right? So we have this. Now what we have is, what you will do is, Now this, what will be the coordinate of this point? It is A, and this is f of A, is it? So the coordinate of this will be A f of A, and what will be the coordinate of this point? It will be B f of B, is it? Now you join these two lines. Now you will join these two lines, okay? Now you will see that on this curve there exists, you can find at least one C, okay, such that here I get a point which is parallel to this line, this chord, okay? So it is parallel to this chord. So here this point is C1, okay? Similarly, if I take a point here, okay, you can see this is parallel here, okay? So this point is C2, right? And at this point also, if I draw the tangent, this tangent will be parallel to this chord. So this is, let me take it as C3, right? Okay. So now you can see that within the interval AB, you will get at least one C. Here we got 3, but at least there will be one C, such that at these points, when you draw the tangent, this tangent will be parallel to this chord. Is that clear? So this is how we write. Now we know that what is the slope of this line. So in the chapter straight line in class 11, you know how to find the slope, okay? If you have a line segment whose coordinate is x1, y1 and whose coordinate is x2, y2, let this line segment be AB. So then the slope of AB is equals to y2 minus y1 divided by x2 minus x1. So this is how you find the slope of a line when you know the two coordinates, okay? So similarly, now here we know the two coordinates of this line, okay? So let it be AB, okay? So we can find the slope of AB, okay? So the slope of AB is, okay, FB minus FA, f of B minus f of A, okay? This is y2 minus y1, f of B minus f of A whole divided by B minus A, right? Since these tangents, okay, are parallel to this line, so therefore the slope of these will be equal to the slope of, so we know that when two lines are parallel, then their slopes are equal, okay? So we have f dash of C1, so f dash means it is the slope of the tangent at that point. So the slope of the tangent at C1, that is f dash of C1, is equals to this. So because these two are parallel, so slope has to be same. So the slope of this tangent is f dash of C1, slope of this line is f of B minus f of A upon B minus A. Similarly, f dash of C2 is equals to this, okay, C2, okay? So the slope of this tangent is f dash of C2. So these two will be equal, slope will be equal, okay? So therefore here we found at least one C within the interval AB, such that the slope such that f dash of C is equals to f of B minus f of A upon B minus A, okay? So this is the geometrical representation of the mean value theorem, okay? Now we will take one example and we will see how to verify mean value theorem. Now it is quite similar to the verification of Rolle's theorem, okay? So I'm going to take one example on this. Okay, now we should see the third example, that is verify mean value theorem for the function fx in the interval 0 to 1. Okay, so now here the steps we are going to follow is same as the previous two examples. Okay, so this is how you will do. Fx equals to x cubed minus 2x squared minus x plus 3 is a polynomial function. Okay, thus you have the two conditions that if a polynomial function it is continuous everywhere, so you have thus fx is continuous on, now you have to write the correct interval. Okay, so fx is continuous on close interval 0 to 1. Number 2, fx is differentiable on open interval 0 to 1. Okay, so in mean value theorem you only have to look for these two conditions, whereas in Rolle's theorem we have to check one more condition, that is f of a is equals to f of b. It is not here in the Lagrange's mean value theorem. So now we'll directly come to finding of c. Okay, so we have f of x is equals to x cubed minus 2x squared minus x plus 3. So that is first you will find out f dash of x. So that is 3x squared minus 4x minus 1. Okay, all right. So you find out f dash of c. So that is 3c squared minus 4c minus 1. Okay. So in Rolle's theorem, what we have is f dash of c is equals to 0. So directly you equate f dash of c with 0 and you get the value of c. But here in this case, in mean value theorem, what you have to do is you have to equate f dash of c with f of b minus f of a upon b minus a. So first you need to evaluate this value. So you will do it here on this side. So what is f of 1? That is f of b. Okay. So it is 1 minus 2, 1 into 2 minus 1 plus 3. Okay. So you will put 1 in this and then you evaluate this value. So 1 minus 1 is 0. Okay. So this is 1. Okay. 1 minus 1 is 0 minus 2 plus 3 is 1. And then you find out f of 0. So this is 0, 0, 0. And this is equals to 3. So now you have to find out f of b minus f of a divided by b minus a. So that is 1 minus 3 divided by 1 minus 0. So that is negative 2. Is that clear? So now you have to equate f dash of c with f of b minus f of a whole divided by b minus a. Now what is your f dash of c? It is 3c squared minus 4c minus 1 is equals to, and this value is equals to negative 2, right? So you have 3c squared minus 4c. When you bring it over here, this will be a positive 2. So minus 1 plus 2 is plus 1 is equals to 0. So using middle term splitting, you can find the value of c. That's 3c squared minus 3c minus c plus 1 is equals to 0. So I'll continue here. Okay. So from this you can take out 3c common. So this is c minus 1. Okay, from here I can take out negative common, so the c minus 1 is equals to 0. So I have 3c minus 1, c minus 1 is equals to 0. So c is either 1 or 1 upon 3. Okay, now our interval is open interval. C should lie within the open interval AB. Here in this case, C should lie within the interval open interval 0 to 1. So therefore this value C will not take. Okay, so therefore we have C is equals to 1 upon 3 in the open interval 0 to 1. Is that clear? So if this function is satisfying these two conditions, then we had shown that there exists at least one C in the open interval 0 to 1 such that f dash of C is equals to f of B minus f of A upon B minus A, right? So therefore you will write at the end, thus mean value theorem is verified. Okay, so almost all the steps are same. The only difference is in Rolle's theorem you have to check 3 conditions and then you have to find the value of C by equating f dash of C with 0. Whereas in Lagrange's mean value theorem, you will check whether a function is satisfying only 2 conditions, and almost all functions will do, because most of the time you will be given polynomial functions, and we know that polynomial function is continuous and differentiable everywhere, right? So you will say that, and then you will check the value, find the value of C by equating f dash of C with f of B minus f of A upon B minus A, and you will always get such C, at least one C in the open interval A to B when a function is satisfying the given conditions. Is that clear? Okay, so this is all about the last topic of this chapter, that is Lagrange's mean value theorem and Rolle's theorem. Okay, so for the concept clarification of these 2 topics, you will do exercise 5.8, not all questions. Okay, I listed out few questions here. You will do question number 1, question number 4, question number 5, and question number 2. Okay, under question number 2 you will see few functions, and for those functions you will verify whether Rolle's theorem and mean value theorem are applicable or not. Okay, so question number 1, 4 and 5, whatever is given in the question, you will do according to that. But in question number 2, under question number 2, you will be given few more functions. Okay, so for those functions you have to check whether Rolle's theorem and mean value theorem are applicable or not, in the same way which we had did here. Is that clear? In the textbook you will see that the question is given in some other way, so you will just neglect that, and you will take the functions given in question number 2, and you will check the applicability of Rolle's theorem and mean value theorem for those functions. Okay, so with this we had completed this chapter, continuity and differentiability, which is the first chapter in the unit calculus. Okay, so in the next class I'm going to start the next chapter, that is application of derivative. Okay, so till then you will try to complete all your works of this chapter, continuity and differentiability, and I hope you had understood this chapter well. Okay, and if you still have some doubts, then you can directly ask me, so I'll try to help you as much as I can. Okay, so with this I will conclude here, and I'll see you in the next class. Thank you.